In this video in our Chemistry of the P-Block series, we're going to be discussing the acid-base properties of the compounds in this part of the periodic table. So if we take a look at the periodic table here, up here on the right-hand corner, top right-hand corner, these elements tend to form compounds which tend to be somewhat acidic in their nature. And as we sweep from right to left of the periodic table, we tend to find a pattern where the compounds tend to become more basic or alkaline in their nature. So examples to keep in mind here would be chlorine, which forms hydrochloric acid, one of the most commonly used of all acids in the laboratory. Sulfur forms sulfur dioxide, which is the compound responsible for acid rain. Another example here might be carbon dioxide dissolving in water to give us weakly acidic solution of carbonic acid. So all the compounds that are formed by the elements in this top right-hand corner tend to be acidic. Whereas in the bottom left-hand corner over here, we tend to form compounds which tend to be basic or alkaline in their nature. So for instance, sodium might form sodium hydroxide, one of the most commonly used alkaline in the laboratory. Potassium forming potassium hydroxide, magnesium forming magnesium oxide, very basic compound. So we have a definite trend in the periodic table from the top right to the bottom left, going from acidic to basic. So as we move through the P-block here then, we tend to see a change from acidic to more basic natured compounds. And in this region here, we can see that there is that transition occurring in the sense that many of these compounds tend to be what we call amphoteric in their nature. So compounds involving aluminium, lead, germanium, tin, etc., these types of elements here tend to show a behavior where they can react with acids and with alkalis. And these are referred to as amphoteric compounds. So if we take a look at some of these to start with, we can look at group 4, which is a good example of the transition from acidic at the top of group 4 down through to amphoteric at the bottom of group 4. So carbon at the top of group 4, forming carbon dioxide, as I mentioned. Carbon dioxide will dissolve in water to give you a weakly acidic solution of carbonic acid. Alternatively, if you take carbon dioxide and you react it with an alkali, 2 lots of sodium hydroxide will form sodium carbonate, whereas 1 lot of sodium hydroxide will form sodium hydrogen carbonate. So this is essentially an acid-base reaction forming a salt and water. Silicon dioxide will behave in a very similar way to carbon dioxide, again acidic, but when we come to germanium and tin and lead, we tend to see this amphoteric behavior where they will be able to react with acids and with alkalis. So if we look at lead at the bottom of the group here, primarily focusing on lead 2 oxide, lead 2 oxide is a giant ionic structure as we would expect. We have a metal here bonding with a non-metal would give us an ionic structure. And this lead oxide is an amphoteric substance. So we can react it with an acid, in this case lead 2 oxide reacted with nitric acid, giving us lead nitrate and water, and that's just an acid-base reaction. Alternatively, we can take the lead oxide and we react it with an alkali, sodium hydroxide in this case, and that would give us this lead hydroxide salt. So group 4 is quite striking in the transition from a non-metal to metal, from acidic compound down to amphoteric compounds. So if you focus in a little bit more on these amphoteric compounds, quite often you might be asked in an exam to discuss the precipitation reactions of these amphoteric compounds, because what we tend to find is that they will form precipitates that redissolve on addition of acid or alkali. So if we show aluminium as an example of this, if we take something like aluminium chloride, which will dissolve in water to give you a clear solution of aluminium ions, and add hydroxide ions to that clear solution, that will form aluminium hydroxide, which is a white precipitate. However, if we further addition of hydroxide ions to that white precipitate, we'll see that precipitate redissolve, giving us a clear solution of aluminium hydroxide with 6 hydroxide ions surrounding the aluminium this time, as opposed to 3. Now, one tip here to try and remember what is a white or what is a precipitate and what is a clear solution is to think of the charge involved on the substance. So here we have aluminium with a 3+ ion. A charged material will tend to dissolve in water. Here the charge is gone because it's been neutralized by the 3 hydroxide ions, and therefore no charge means it tends not to dissolve in water. Over here we have the charge back again because now we have 3 extra hydroxide ions, so we have a 3 negative charge, and therefore the charge means that that substance will dissolve again. Obviously we can reverse this by the addition of acid, so if you add acid and H plus ions to the clear solution, you will reform the precipitate of aluminium hydroxide, and you would form water molecules in that process as well. And if you keep on adding acid to that white precipitate, you can form a clear solution again of aluminium ions and more water molecules. Now when you look at this sequence of reactions, you might be thinking, well, how does this relate to amphoteric behavior? And it becomes a little bit more apparent if I blank out a couple of these arrows. So if we look at aluminium hydroxide here in the middle, this is the amphoteric compound in question because it can react with an alkali to give us a clear solution of AlOH6-3-, but equally it can react with an acid to give us a clear solution of aluminium ions. And so it's the aluminium hydroxide here that's the amphoteric compound. We can see similar patterns with lead. As we talked a second ago, lead is another amphoteric, or lead compounds tend to be other examples of amphoteric compounds. And so if we take lead ions, now it's quite difficult to get lead ions to dissolve in water. Most lead compounds tend not to be soluble in water, but lead nitrate is. So if we took a solution of lead nitrate, that would give us a clear solution. And if we add hydroxide ions again to this, we would form a precipitate of lead hydroxide, a white precipitate. And again, notice charge is dissolving, no charge is not dissolving. And we can keep on adding hydroxide ions to this, just as we saw with aluminium, and that white precipitate will redissolve to give us PbOH4 2-. Now we have a charge on this compound again, it dissolves in water. And again, we can reverse this process by the addition of acid, taking our clear solution back to our white precipitate, and then keep on adding acid will cause that white precipitate to redissolve again to form our lead 2+. That's obviously bearing in mind if these are nitric acid, the H plus ions are coming from nitric acid, we will form lead nitrate, which is a clear solution. And again, if you're struggling to see the amphoteric nature in these sequence of reactions, blanking out these 2 arrows shows you that it's the lead hydroxide in the middle here, that's the amphoteric compound. Adding an alkali to it gives us a clear solution of lead hydroxide with 4 hydroxide ions surrounding. Adding an acid to it removes the hydroxide ions and gives us Pb2+. So it's reacting with an acid, and with an alkali. Okay, I just want to also discuss here lead-2 precipitation reactions in general. Now this is not acid-base in nature, but lead-2 precipitation reactions is a common question on the exam papers. And as we are talking about lead forming a precipitate, we may as well cover this here. So as I mentioned, lead nitrate is one of the few lead compounds that actually will dissolve in water. So if we take a solution of lead nitrate, we can add various ions to this, and we can see the precipitates forming as we do so. So if we take lead sodium hydroxide and add it to our lead nitrate, then we can see that we form a white precipitate, just as we mentioned a second ago. However, what I didn't do when I was recording this video, stupidly, was to keep on adding the hydroxide ions, because if I was to keep on adding hydroxide ions to that test tube, then we would notice that the precipitates would redissolve and would go back to a clear solution of our PbOH4 2-. And obviously, as we mentioned a second ago, adding acid to this would reverse all these equations. We can also add chloride ions to our lead nitrate solution. And if we add chloride ions again, we form a similar white precipitate. This time, however, the lead chloride that we form does not redissolve. You cannot include any other chloride ions around that lead to form a clear solution. We stay with the precipitate. And then the final set of precipitation reactions that we can do with lead nitrate is we can add potassium iodide. Now this is very striking. It forms this beautifully vivid yellow precipitate of lead iodide. And again, this doesn't redissolve, I can keep on adding the iodide ions as long as I like here, and I will not get it to redissolve. PbI2 is our solid compound, that beautiful yellow precipitate. So there we go. That is the acid-base reactions of group 4, and also led to precipitation reactions added onto that. So complete that in your booklet now, and make sure that you have a go at some questions so that you know how to tackle these if they were to appear in your exam.